speaker is Yihong Wang, and her topic is Hopf algebra, Nichols algebra, and straight BCJ relation.
Well, that's not my slides.
Oh, sorry.
So I just want to talk about our effort in exploring the connection between string BCJ relation and well-studied quantum algebraic structures, and and to see if such mathematical understanding would help us in understanding the physics of string amplitude, and if it can help us to calculate these things more efficiently. And so here is a review of definitions of BCJ relation. So BCJ relation is a non-trivial linear relation satisfied among open string amplitude that's related by commutations. And the linear coefficients here are what we call momentum kernels. It has a form of successive product of sign of Mandelson variables, and the specific form depends on the commutation you are looking at. Here's a 4-point example, and it has been shown 10 years ago that BCJ relation would be part of the string monodromy relation, which is a natural result of the form of string amplitude and conformal symmetry. Here is a 4-point example as well. If you're familiar with spin chains or quantum algebra, you probably already see you're already seeing the quantum shuffle or grading structures here, but there are more evidence pointing in that direction. So this is our previous the results of our previous work, and we found that the BCJ sum or BCJ relation can be written in form of the successive deformed commutators of these screening vertex operators. And so these are the evidence that convinced us to take a serious look at the quantum algebra and to articulate what exactly are the connections. And so here are some definitions I'll need to show you the framework of these things. And so basically, quantum algebra is a Q deformation of the algebra. And there's a version of definition for the algebra that uses only Cartan sub-algebra and the simple roots, as well as the series relation. So quantum algebra are usually written in forms of Q definition of this version of definition. And so you can see the quantum series relation, more manifest way to show this is a quantum series relation is to write all these relations as the successive Q commutators of the simple roots. And we also need the definition of its enveloping algebra, which is basically the tensor algebra that moduli whatever identities you have in the quantum algebra or the algebra. And so the universal enveloping algebra can be described using the language of Hopf algebra, which has a product to allow you to extend the length of elements, and a co-product to taking to account for whatever commutator or Q-deformed commutator in that algebra you're talking about. And also it has the unit, the co-unit, and the antipole, which is more or less a generalized version of the inverse. So here is an example of writing quantum algebra as using Hopf algebra. And sorry. So this is the last definition. We also need the definition of the Nichols algebra, which is a special kind of Hopf algebra that's closely connected to our discussion for the string amplitude today. So it starts from, it's constructed from a braided vector space, which you can think of as a spin chain with the action that permutes two adjacent states and with a face. And with this section, you can define the so-called quantum shuffle map, which is basically a total symmetrizer with the face that comes in with the braided vector space. So with this quantum shuffle map, we can work out the kernel of this map. Usually, if there are linear relation between the braiding faces, there will be non-trivial kernel of this map, and the Nichols algebra is just the full tensor algebra moduli this kernel of this quantum shuffle map. And so in the 90s, people in quantum algebra community find that that actually the positive part of quantum algebra can be constructed from this Nichols algebra construction. So that is, if you take the braiding vector space to be with the braiding face that comes from the Cartan matrix of the corresponding quantum algebra, then you will get the kernel of the shuffle map is exactly the quantum serial relation of that quantum algebra. So that's also the same the algorithm that we use for our open string amplitude. So what we do is that we look at string amplitudes as a spin chain or a braided vector space, and the map from amplitude to numerator is basically just the quantum shuffle map, and the linear combination of this form for the amplitude constitute the kernel of that quantum shuffle map. So basically, what we found is that the BCJ relation is a form of generalized quantum serial relation, and the momentums in that the momentum within those amplitudes are the simple roots of the algebra, Here is a outline of the story. So up to the third step here is the Nichols algebra construction. So we start from the monotony sum, and that will be our component symmetrizer. And we found our kernel to be the BCJ sum, and that will be our component serialization. So that the algebra of screening vertex operators are the positive part of some quantum algebra. And so after that, we need to, for quantum algebras, we need to do all the things such as doubling to get the negative roots, and calculate all the commutators and deform commutators to get the non-simple roots, the Cartan sub-algebra, and all other elements in these quantum algebra. And so in physics, these are the OPEs and annihilation operators. And after we get the full algebra, we'll get what physicists want the most. Like, we can write string numerators as structure constant of some algebra. And most of the problems that concerns physics and most of our work are like focused on these two steps. Also, you can take the alpha prime limit, or where the Q goes to one limit, to get the field theory numerator. And that's pretty much what we want to do. And I haven't. We have some simple some result for a lower point that's already showing some pattern and consistency with previous results on string amplitude. And I haven't shown you any details of them yet, but I hope you enjoy the story. And that was my talk.
Questions?
The string amplitudes you are considering are open string amplitudes.
Yeah.
Is there a general application to full string?
That's part of the story that we haven't understand yet. We think the double quality would be related to the co-product action in the whole algebra, but we haven't worked that out yet. So that part I don't have anything.
So what is Q?
Q is an arbitrary parameter.
It's from string theory side.
That's e to I pi alpha prime.
So what happens if Q root of unity?
Well, that will pretty much be similar to the story in quantum algebra.
So representation should be very well restricted.
Yeah.
So what's the implication of that instance?
Well, there are early works of that sort that to get the symmetry group from string amplitude. And if you have a root of unity, the group will be much more simplified, and you can construct.
No, proof is saying representation is restricted.
No, I don't think that the group will be the same. For root of unity.
Your computation ratio is same, except when you try to find a representation of those theories, then usually they are restricted.
Okay. So won't that be simplified? Like, well, the part I know is that if everything is integer, and you can calculate the algebra out of it, and that's a way like
another question? Let's thank you.